Okay, very good. Welcome to the second day of Serverless workshop, our second edition. We will be starting session 4 and then session 5. And we have recording for the previous day. So I will be encouraging everybody to check the recording, and I will be going really fast. We showed that yesterday as well. So that's, you should be checking our future workshops. And if you are interested, you can see the previous workshops as well. We will having WOSCx1 at the end of the year with middleware. Check our call for papers soon, and please subscribe to our mailing list for future announcements. And also, if you want to send something to other people interested in serverless computing. And everybody here should be also in the Discord channel. So if you did not do it already, please post in introductions, if you want to advertise what you are doing. And any questions related to WOSCx2, we have the dedicated channel for it. Also, you can post your slides or any other links you want. We talked about it yesterday, so I will just say that we want to expand the serverless as it is no longer about function as a service, but everything related to building great experience for cloud and any other place where you want to run code. All the presentations will be 10 minutes. That's the maximum time. Maybe it's already too much because we split the workshop into 2 days. If you want to ask questions, just ask them in Discord in asynchronous way, or put a comment in Zoom, or raise your hand if the speaker makes available time for actual questions in Zoom. It's up to speakers to decide, if they want to use 10 minutes to talk or leave some time for questions. Pedro, can you say a few words about the polls we were doing yesterday?
Yeah, summarizing the polls yesterday, you see in black the WOSCx1 in June 2022, and in the left you see with background white, you see the polls for this year. So in 1 year we have more participants, but we also have more insights. You see some common topics. So state is very big in both years, in June 22, June 23. Latency is in both of them. Programming abstractions, I'm not sure, yes, usability probably. So the billing is also in both of them. So we can identify in these 2 slides, in these 2 plots, some common terms for both years. Even if we are seeing some new things in 2023 that goes further with things like lack of SLAs, application topologies, then edge and others. So these are the challenges. If you move to the next slide, then we see the second question. We will be asking this question every workshop to see where serverless is heading. So here again in black 22, in white 23. In black, last year the future of serverless for our community was hybrid and cloud continuum. It was edge. It was distributed function as a service composition. This year, I think we've seen here different futures for serverless. Serverless everywhere. So now people consider that serverless can reach all the deployments in computing, not only hybrid, but anything. Single abstraction, multi-cloud, and now new things, of course, ChatGPT, LLMs, AI. It's becoming big. We begin to see this in the future of serverless computing. So if this appears this year, let's see in 6 months and in 1 year what we will see as future of serverless computing. But certainly this is not a dead topic, and we are really moving on.
Okay, thank you. So we can start with the actual presentations. I think the first one is the playback, right, Paul, if I remember correctly?
Right, yeah, so we have, I think we have 4 talks in this session. And the first one is from Herbert. from the Technical University of Munich, and unfortunately he can't be here today, so we're going to play his video.
Okay, so we tested and it seems it worked for me, but not for you, Paul. So I'm going to
Yes,
screen share
correct.
and play it back. Let me know if the playback or there are any issues that you cannot hear.
Hi, my name is FLEdge. Today I will be talking about FLEdge, benchmarking federated machine learning applications in edge Kubernetes. So this is a work that's currently in submission, and a paper preprint is already available on arXiv. So before we get to it, a few words about myself. So my name is Herbert. I'm a research associate at the Technical University of Munich. My research focus is federated machine learning systems in resource-constrained environments, i.e. edge computing systems. Furthermore, I'm working on an industry project that deals with federated non-invasive condition monitoring for industrial processes. And I'm also responsible for managing our 2,000+ CPU core private cloud, including some GPU servers and an entire edge computing testbed. So at the beginning, I want to introduce federated learning very briefly. Why do we need privacy-preserving machine learning? Well, first of all, if we think about machine learning in general, what we do is we first of all collect data in a central place. We pre-process it in that central place, and only then we train our machine learning model. However, this comes with a lot of privacy related challenges, especially when we think about systems where we have many users, each holding very little data. So for instance, hospitals or people owning a car, right? And there we often have the problem that we can't get the data from the users, so we can't train our machine learning. What can we do against it? Well, in 2017, federated learning was introduced with a technique called federated averaging. This is what I will explain on this slide. So first of all, we as machine learning engineers, we design our model that we want to train. And in federated learning, we now don't train it ourselves, but we put it on a server. And we allow clients, so the users, to register. And each client holds very little data that can be used to train that global model. So the server sends an update to the user, sends a model to the user. The user does all the training on their local device, and only then the user sends back an update to the server. Once every user that was selected for training run has done that, these model updates are being aggregated into a global model, i.e. our model we initially developed is getting updated with trained weights. And one very popular technique is federated averaging, basically where we would average every single model weight with among the client updates. And we repeat this over multiple rounds, because through this round-based mechanism, we achieve model convergence and a very competitive training progress as compared to central machine learning as we know it. So today, I want to talk about FLEdge. FLEdge deals with 4 major points. Number 1 is resource heterogeneity. Number 2 is energy efficiency, 3 client reliability, and 4 data privacy. In this short talk, we will be focusing on resource heterogeneity and energy efficiency. And I will briefly discuss our key insights. So first of all, when we think about hardware heterogeneity, what we see here is the time it takes for a certain device type to process one batch of data in a deep learning model. We also evaluated various model architectures, and what you see in brackets is the number of parameters that a model has. And what is noteworthy is that with increasing model size, we see a exponential growth in processing times, especially on embedded devices, which are the Raspberry Pis here. We also have another type of embedded devices, the nanos. So these are NVIDIA Jetson nanos with 128 GPU cores. And what we see is their runtime still increases, but not exponentially, which suggests their ability to handle a lot more complex deep learning models than the Raspberry Pis. What we find in our experiments is that the hardware acceleration on the nanos speeds up the training process by 16 times. And what you see here are state-of-the-art federated learning workloads. Yeah. So we see the importance of adding hardware acceleration to embedded devices. And one further topic that goes very closely along with that is energy efficiency. Here we again have the same x-axis and a different y-axis. Here we now measure energy efficiency as samples per second per watt power draw. So basically, how many samples can we process when consuming 1 watt of power? And what we see here is we can process 96 samples per second per watt power draw on the nanos, while only 33 on the GPU. In total, the GPU can draw up to 300 watts, so it is much faster than the nano, while the nano can only draw 50 watts. But still, we see in terms of energy efficiency, the nano is 3 times more efficient. And when comparing the nano embedded device against the Raspberry embedded device, we see it there's also almost 4 times, the nanos are 4 times more energy efficient. So what we want to express with that is that energy efficiency plays an integral role in federated learning research, but the way it is done today mostly addresses new methods and sort of better aggregation techniques, but neglects the fact that energy efficiency or the workloads that we train with are better suited for embedded settings. And this can help us reduce energy consumption by a lot. So that was a quick overview of the first 2 main results in our paper. To conclude, what do we learn about resource heterogeneity? So resource heterogeneity has a 16 times performance impact when comparing different embedded device types. When we transfer that into the real world, we need to consider that many applications are bound to industrial processes. So evaluations must consider these industrial processes, and they are often characterized by very long life cycles and that they contain legacy devices, so without hardware acceleration. And therefore, we need to include these legacy devices, such as Raspberry Pis, in our evaluations for federated learning workloads. Secondly, energy efficiency. Well, we show that hardware accelerated embedded devices are consistently a lot more faster than non-hardware accelerated embedded devices. And therefore, also with sustainability in mind, we need to consider the evaluation of federated learning workloads on embedded devices. So this was a very brief talk. If you're interested in more details, please have a look at our preprint. I'm very much looking forward to feedback, and otherwise, always happy to answer emails. Thank you.
Okay, great. So I think the next talk is from Jawad. He's also from the Technical University of Munich, and he will present his work on streams under test. So Jawad, take it away.
Thank you very much, Paul. So, welcome everyone to my talk. My name is Jawad Tahir, and I am doing my PhD at Technical University of Munich. And today I'll be presenting my ongoing research, which is titled Streams Under Test. And in this study, we do performance, correctness, and the recovery study, or recovery benchmarking of stream processing system under different failures. First, let's build the motivation that why are we benchmarking distributed stream processing systems? So as we all know that the data volume and velocity are increasing over the years, over the past couple of years, and the trend is continuing to go upward. In the same time, we see that the processing power is hitting a plateau, and the processing power is not improving as it used to be. So now we have increasing amount of data and we have a decreasing amount of processing power upgrade every year. So what we do, we create a network of many machines and we distribute the data between these machines so they can process it. And if we want to process more data, we add more machines to our network, and yeah, it continues and it scales horizontally. And now the second question is like, why are we doing benchmarking, failure benchmarking? So the reason is that the failures are inherent in distributed systems. If you remember the CAP theorem, it tells you that in the case of in any distributed systems, one can only choose between consistency and availability in network partitions, which underscores the omnipresence of failures. And these failures can cause catastrophic damages like data loss, incorrect results, performance degradation, and whatnot. And also, Beru reported to have more than 290,000 faults in their infrastructure in 4 years, which equates to about like 200 faults in a day. So this shows that failures are omnipresent and everywhere, and that's why we're testing the benchmark. That's why we're benchmarking stream processing systems. We also conducted a bit of study where we saw, we have many distributed failure, and then the reasons that why these failure occur. That's summarized here. I will not go into details here. And then let's do a bit of background on stream processing systems. Stream processing system process the unbounded data as compared to the batch processing system, which works on the historical data. So I mean, this data can be anything. It can be tweets, it can be clicks on your website, it can be taps on your application, it can be sensor ratings, and they provide us real-time insights or trending information, which we can see in any application that we use today. And then the processing in a stream processing system is defined by a graph of operators, and which is also called topology. And these operators can be of two types. One is stateless operators and one is stateful operators. Stateless operators are those operators which do not have a history of previous events. For example, if we would just want to amplify a signal, we will just like multiply it by a constant, and that's pretty much it. But on the other hand, we have stateful operators, which needs to know the history of some events that has been gone through this operator. For example, we can do moving average. In moving average, we need to know that how many events have passed in X minutes or X time. Now let's do a bit of background on the recovery and the processing guarantees. Recovery means how does a system recover after failures. In terms of stateless operators, quite easy. We can just like restart an operator. But in terms of like stateful operator, which contains a state or contains a history of some previous event, there are like multiple ways how we can recover from after a failure. For example, replaying state updates, or using snapshotting and storing it on some persistent storage, and then reinstating this state after the failures. Or we can use RDDs, redundant distributed data type. And then we have processing guarantees, which tells you like how a system ensures correctness during failures. And there are like 3 types of processing guarantees at most once, which means that any event or any data point will not be processed more than once. It may happen that one data point is not processed at all, but it will be processed at maximum once. Similarly, we have at least once, which tells us that every data point will be processed. It may happen that a data point is processed twice, but there won't be any missing misprocessing in the data. Similarly, we have exactly once, which tells us that every data point will be processed exactly once. It will not be processed twice, and neither it will be skipped. Every data point will be processed exactly once. However, these processing guarantees are only provided when the data source that we are reading the data from also provide these processing guarantees. Now I will show you my benchmarking design. So there are like multiple things in my benchmark design. Let's first have a look at the workload. Our workload consume two streams. One is the click stream and the other is update stream of a web resource. And then it ingrests these streams and then join them and then do a group by and then do a window and then outputs the events. And what it does, it counts the number of a time a resource is accessed or updated in 1 minute. And then it's and then we are using Apache Kafka as our source and sink. So yeah, it's Apache Kafka is a streaming engine, and we are using Apache Kafka as our data source and also a data sink. And then let's talk about the data set. We, as I shown in the previous slide, we're consuming two streams. One is click stream and the other is update stream. And we are using synthetic data set so that we have a controlled output. And this data is disseminated or distributed or generated through a data generator. And the data rate of this data generators can be throttled or can be varied. And we are running data generator at the speed such that we have the lowest latency. If we cross this point, then our latency, events starts to queue up, and at the latency that we have starts to explode. So we're running at the maximum data rate such that it gives us the lowest or the stable latency. And this is the architecture. We separated the system under test from the benchmarking utilities. And this data generator writes the data into Kafka cluster. This streaming system consumes the data and writes it back. And then we use a Pumbaa server, which is the utility to inject failures into our system. This shows our experiment workflow. At T0, we deploy our source and sink and the topology. And at T1, we start our data generator. And then at T2, we introduce failure or inject failure into our system. And at T3, we remove the failure. And at T4, we stop the data generator. So we can divide our experiment into three phases. First, the before failure, during failure, and the post-failure phase. And we selected three frameworks to benchmark our work. So we use Kafka Stream, Apache Flink, and Apache Storm. Now let's have a look at some results that we obtained in our benchmarking. So in this graph, we injected process crash. We crashed one of the nodes in our system, which is highlighted with the black line. And we saw that when we injected failure, it stopped processing, and the workload of this node was distributed to the remaining nodes in the system, and it continued to process the streams. And here we are injecting 20% packet loss into our system, and we see that when we injected the failure, this affected node still continued to process, and its workload is not transferred to the non-affected nodes. Hence, that's why we're seeing a very high increase in latency and a very significant drop in throughput. However, we conducted another experiment where we injected 80% of packet loss. And here we can see intuitively it would make sense that the results that we obtained are worse than the 20% packet loss. But we saw that our results are getting better because what system is doing, it's taking this system as a process crash, and the processing of the affected node is transferred to the non-affected nodes. Hence, that's why we see a lower latency spike and a lower throughput drop as compared to 20% packet loss. And similar results can be obtained for the packet delays. And then these are results for our Apache Storm. And here we see interesting thing that the latency spike that we experience is much lower than the previous one, than the Kafka Storm that we benchmarked. And then here we have an Apache Flink, and here we see an interesting result. When we injected a failure into one machine, the whole system stopped working, which is quite interesting because in the previous system, when we affected one node, the workload of that node was transferred to the other non-affected nodes. But here, when we injected failure into one node, the whole system stopped working. So I'll summarize my results here. So every streaming system has its own strengths and weaknesses. For example, Apache Flink gave us the lowest latency, so it can be used in a time-sensitive application. However, it halts the processing when there's a failure in the system. So how to fix this thing? We can have some redundant workers in the system. So here in the graph, I've shown that when we have redundant workers in the system continues to operate without any significant changes or significant drop in throughput or latency, and it does not offer any processing guarantees. Similarly, we have Apache Storm, which has the least impact on latency during failures, and it handles partial failure better than the other two systems. And then it provides only at least once processing guarantee in partial failures, and Kafka Stream have a good balance between throughput, latency, and correctness, and it is the only DSPS to provide us exactly once processing guarantee. And it handles process crashes better than partial failures. So if you're experiencing some partial failures like 20%, some packet loss or some packet corruption or some packet delays, it's just better to kill that node where experiencing this failures, so it can divide the work or transfer the workload to the non-affected nodes. So if I summarize the whole presentation, my whole work in like one liner, it would be that processing guarantees that these system claims to provide, they should come with an asterisk, because these processing guarantees are not valid in every failure scenario. So with that, I conclude my presentation. If you have any questions, please feel free to ask.
So any questions for Jawad? I guess if not, we can move on.
Mm-hmm. Thank you.
Thank you, Jawad. So our next talk is from Aitor. He's from University Rivera in Spain, and he's going to talk about caching large temporary data in serverless workloads. So,
okay, can you hear me? Can you see the screen?
Looks good, and I can hear you.
Okay, thanks. Okay, yeah, my name is Aitor Arjona. I'm a PhD student in Universitat Rovira i Virgili, and in this talk, I'm going to present caching large temporary data in serverless workloads with a collocated ephemeral store. This work has been done in collaboration with IBM Zurich Research in the context of the Clusters Research Mobility project. So first, I'm going to skip this introducing serverless because I hope everybody here knows about it. But what I want to make emphasis in that serverless services and infrastructure are evolving compared to maybe 5 years ago. We now have more resources, for instance, more CPU and more memory available, lower overheads, and also other new services like serverless Spark. And this means that serverless is now broadened more every year for its applicability for more applications. But there is still a major problem that is handling temporary data, that it's the data that it's produced between workflow stages. So the problem is that serverless is a data shipping architecture, which means that temporary data has to be passed through slow disaggregated storage. And here I want to reference this very controversial post from the Prime Video development team because they have this application that writes to S3. They write a lot of video frames to S3, and this is it's not only a limitation in scalability, but also produced a lot of cost. So we see that it's still a major problem. So the proposed solution here is to enable serverless functions or containers to access to a shared global collocated ephemeral storage. So first, we have this current approach in which each container has its own private ephemeral storage here and has to access object storage to pass data around. In contrast, the proposed architecture, in the proposed architecture, we have a share volume for each container running in the same node, but also containers can access the volume of other nodes in the cluster. So here, the proposed improvement is mainly to leverage locality for collocated workers in the same node. And we want to target the implementation on Kubernetes workloads. So the main idea is to share data transparently between pods in the same node by using a shared volume mount binds, but also with data, but also share data with pods that are running in other nodes in the cluster. So the main benefits would be that we can share data between concurrent containers, but also with subsequent containers if we keep the volume warm for a small window of time. So we can also cache data from S3 and access it using file-like semantics. And finally, we can stage. We can use this storage as a staging for warm output data before it's being persisted to object storage. However, here we have some challenges, mainly security and isolation. Because since we are breaking container boundaries and sharing resources, we have to keep security and isolation as a first priority. But also, we don't want to hurt performance in order to keep the security. So also the system has to be performant. And finally, it has to also be elastic, because in serverless workloads, we can have many containers being allocated and deallocated very fast. So the system has to also be elastic accordingly. So one important thing is that temporary data is ephemeral, which means that it can be regenerated by rerunning parts of the workflow. So this means that temporary data can be stored in a system that relaxes persistency but offers high throughput. And in this context, we plan to leverage GEDS, which stands for Generic Ephemeral Data Store, which is a storage middleware for ephemeral data that is being developed at IBM Zurich Research. So the main trait of this storage system is that it's cost effective because it runs co-located within the compute cluster, which means that there's no need to provision more resources for storage. But it also implements a tiered architecture in order to accommodate large data and also enable elasticity. And finally, it integrates with cloud object storage for caching and persistency. So talking about the implementation prototype, we have some challenges because in Kubernetes, the storage design is disaggregated to enable high availability and scalability. So pods are accessing network flash systems or block storage like in Ceph. However, what we want is to leverage physical disks for ephemeral storage on ephemeral worker nodes. Basically, we have two main mechanisms in Kubernetes to do that. The first is mounting host volume paths in pods, but this is not recommended because there are many vulnerability issues related to it. And the second alternative is to use CSI driver, which this driver can implement logic to bind mount volumes to containers of the same tenant running at the same node. So with this approach, we have better security. We also run some benchmarks in order to compare the viable approaches to see that there are no performance penalties. Now, another interesting approach with these sharing volumes is that we can memory map files in order to share memory. So memory mapping is a mechanism of the operating system that allows zero copy access to the underlying file buffer in memory. And the interesting part here is that since we are sharing volumes, different containers can memory map the same file stored in a shared volume mode. And interestingly, the C group's memory management only accounts for processes which write to the memory map. So this means that we can share data that is read-only, for instance, a machine learning model that is being used as inference. And this is a safe approach for memory sharing between containers in Kubernetes. And finally, we also proposed a use case for this approach based on a serverless variant calling genomic pipeline. Here, this pipeline has complex data movements and high data utilization between tasks and different access patterns, like one object that is consumed by many tasks, or also a Cartesian product of two datasets. So this pipeline is a good example of how we can exploit this system. And we have implemented some access patterns in order to test this approach. First, we have the one object many task and Cartesian products of two datasets, and we can see that the caching from object storage reduces in part the fetch time of the data. So to conclude, we can say that serverless workloads with high data utilization and sharing can benefit from efficient temporary data storage. Also, temporary data can be stored in an ephemeral data store for better performance. And we propose a co-located ephemeral storage for serverless systems that provides high performance, throughput, and cost efficiency. Finally, we propose architecture for leveraging locality in Kubernetes serverless systems. And we proposed a validation using serverless genomics pipelines. So thank you for listening. That's all.
Thank you, Aitor. Any questions? I see a hand raised. I can't tell who raised it though. Bartosz.
Yes, hi. Very interesting talk. So I have a question, because you can use NFS storage as an ephemeral storage exactly in the way you described. So why did not use it simply?
Sorry, what kind of storage?
I said that you can use NFS storage as in ephemeral way. Yes, that's exactly how you described, leveraging local disks. So why did you not use NFS?
Yeah, so we also want in part not implement a full POSIX file system. So what we want to do also is to have like a key value store that has file semantics in order to have better performance.
Okay, thank you.
Any other questions? If not, thank you, Aitor. I think
Okay.
great talk. We have our last talk of this session is from Ben Carver, who's a PhD student at George Mason University, and he'll be talking about Lambda FS. So Ben, take it away.
Okay, let me get my screen shared here. Okay. All right, I think we should be good to go here. Okay. So, hi everyone, my name is Ben Carver. I'm a second-year PhD student at George Mason University, and today I'll be giving a talk on our research project entitled Lambda FS, a scalable and elastic distributed file system metadata service using serverless functions. So first, I'll briefly give some background before going over the project's architecture and design. So serverless computing is a new emerging cloud computing model that enables a new way of building and scaling applications and services. Developers can break traditionally monolithic server-based applications into finer-grained cloud functions. And there are several key benefits of serverless computing. We have elastic auto-scaling, or the ability to scale out to hundreds or thousands of instances very quickly. There is a pay-per-use pricing model in which users are billed using a fine-grained pricing model that only charges them for the resources that they're actively using rather than just what's provisioned, and automatic resource management, by which the cloud provider manages the servers that the functions are hosted on, relieving users of the notoriously tedious tasks of server configuration and management. The metadata service, or MDS, sits on the critical path for distributed file system operations, and therefore it is key to the overall performance of the large-scale distributed file system. But scaling the MDS is difficult, and existing scaling techniques, such as using a cluster of metadata servers, for example, lack elasticity, require tedious server management, and they may suffer from high costs and low resource utilization. So then the question is, Can we use serverless computing in a novel way to build a high-performance, cost-efficient, elastic, and resource-efficient metadata service? And the answer to that is yes. We've designed and implemented Lambda FS to demonstrate this. In a nutshell, serverless functions are an appealing environment in which you can host the metadata service of a large-scale distributed file system. The elastic auto-scaling provided by serverless computing enables the metadata service to automatically and dynamically scale to the workload in real time, and it also improves cost efficiency, resource utilization with the on-demand resource allocations and deallocations. And likewise, the pay-per-use pricing model can drastically lower tenant-side cost while not negatively impacting performance. And then finally, the automatic resource management and provisioning simplifies the deployment and configuration process of the distributed file system. So next, I will quickly go over the design of Lambda FS. Lambda FS has been ported to both HOPS-FS and HDFS-based distributed file system and BGFS and IndexFS, so as to demonstrate its generalizability. So this diagram here shows the project architecture of Lambda FS running with HOPS-FS. Essentially, clients will issue metadata operations to the serverless caching layer, which consists of a dynamic layer of elastic serverless name nodes. These name nodes are responsible for caching and serving the file system metadata from the persistent metadata store and then their local caches. This coordination service provides a medium through which the serverless name nodes can coordinate and synchronize in order to provide strong consistency for distributed file system metadata. And finally, clients can read and write file contents that are stored on the DFS data nodes. There are two key design components of Lambda FS that I'm going to discuss. The first is the hybrid fast optimized TCP HTTP RPC mechanism, and the second is Lambda FS's fast-based metadata caching layer. So Lambda FS clients use a hybrid TCP HTTP RPC mechanism to communicate with serverless name nodes. Traditionally, HTTP requests are used to communicate with serverless functions, and these requests are typically routed through one or more components of the serverless platform, such as an API gateway, and consequently, they can incur high latency. Because of this, Lambda FS clients also use TCP connections that are directly established with the name nodes to perform a majority of their operations. So for this process, clients will first issue a standard HTTP request, which will be received and processed by a given serverless name node. Once that request has been processed, the name node will establish a TCP connection back to the client using network information that was included in the HTTP payload. And from that point forward, future requests will be predominantly submitted over this TCP connection. They'll have lower latency and improve overall performance. But occasionally, Lambda FS clients will still issue HTTP requests based on a configurable probability. And this serves to essentially keep the serverless platform in the loop, enabling elastic auto-scaling to occur when the request volume increases or decreases. And so together, these TCP requests enable low latency, while the HTTP requests enable a precise degree of auto-scaling to occur. And this helps to maximize both performance and cost effectiveness. Next, we have a fast-based metadata caching layer. Lambda FS uses this fast-based metadata caching layer to drastically reduce the end-to-end latency of individual file system operations, essentially by just reducing the bottleneck of accessing the persistent data store. So if you look at this diagram on the bottom here, a Lambda FS client may issue a metadata request for a file like homework.pdf. If the name node that receives this request has the metadata for homework.pdf cached locally, then a cache hit occurs at step 2, and the metadata is returned back to the client immediately in step 3. This client may then issue another metadata request for a different file like notes.txt. This request may be routed to a different name node as shown in step 4. And if that name node does not have the metadata for notes.txt cached locally, then a cache miss occurs like we see here in step 5. In this case, the name node will access the metadata from the persistent data store, cache it locally, and then return it to the client in step 7. So I will briefly go over a few of the results from our experimental evaluation of Lambda FS. And this first result comes from our industrial workload experiment where we ran the Spotify HDFS cluster trace, the same trace that was used to evaluate HOPS-FS that I mentioned earlier. Essentially, we issued random file system operations that were generated based on the distribution of operations from the trace, which is shown in this table here. We also wanted to evaluate our elastic auto-scaling policy. And to do this, we modified the workload to randomly generate bursts of requests with throughput up to 7 times the base throughput. And this chart in the lower left here basically plots the instantaneous throughput for each second of the 5-minute Spotify workload. We evaluated Lambda FS, we evaluated hops FS, and then we evaluated another version of hops FS in which we modified the name nodes to also cache data locally so that we could better elucidate the impact of Lambda FS's metadata caching layer. Results for Lambda FS are shown in red, the results for hops FS in blue, and hops FS augmented with a cache in green. We also plot on the secondary y-axis the number of active serverless name nodes used by Lambda FS. You can see that with this gray line here. The base throughput of this particular workload was 25,000 operations per second, and all frameworks used a total of 512 vCPU. And as you can see, the main takeaway here is that both versions of hops FS were not able to sustain the throughput of the workload as generated. Specifically for the hops FS plus cache version, during this burst right here, this large burst of about 164,000 operations per second, hops FS could not complete the workload as generated, but Lambda FS was able to complete the workload as generated by provisioning additional serverless functions in response to the increase in request volume. It provisioned an additional 12 serverless name nodes, and in doing so, it was able to complete the workload as generated. We also created a new performance per cost metric to evaluate the cost effectiveness, which is just instantaneous throughput divided by instantaneous cost. So the units are throughput per dollar. We have this chart on the right here, plotting the performance per cost for hops FS plus cache and Lambda FS for the same workload. And as you can see, Lambda FS is able to achieve a significantly higher performance per dollar. This is because of its resource efficiency by using a bunch of small serverless name nodes to serve the metadata operations. We're able to better utilize the underlying resources. We're able to use less resources while still delivering good performance. And this in turn leads to better cost efficiency. We also leverage the pay-per-use pricing model to avoid paying for idle resources as well. So next we have some client-driven scaling results. We basically just varied the number of clients from 8 to 1024 for a bunch of different file system operations. These two charts here showed read and list. We have several server full baselines. We have hops FS plus cache, and Ceph FS. As you can see, Lambda FS here achieved the highest throughput of all of the frameworks tested. Compared with vanilla hops FS in particular, we achieved 28.91 and 20.53 times higher throughput than hops FS for read and LS respectively. We also outperformed hops FS plus cache and Ceph FS. And we also outperformed InfiniCache, which was a serverless function-based object store. And this performance difference is because of Lambda FS's ability to auto scale effectively. So as the number of clients increased in this test, the number of name nodes that Lambda FS used increased, and that enabled us to achieve better performance. So in conclusion, Lambda FS is the first cloud-native distributed file system metadata service that uses serverless computing to cache and elastically scale distributed file system metadata. Lambda FS can achieve high throughput, low latency, low cost, and high resource efficiency by utilizing a series of techniques built around this fast-paced metadata cache. We ported Lambda FS to both hops FS and index FS, and we hope that this will provide insight for building new cloud-native, performance-sensitive backend services on serverless computing. Lambda FS is set to appear in ACM ASPLOS 24, and there is a preprint available in archive. The source code is available on GitHub, and you can find additional information on our lab group's research page. Again, my name is Ben Carver, and I would be happy to answer any questions if you would like to contact me. Thank you.
Thank you, Ben. Any questions? I had one question about cold starts.
Sure.
Did you have an issue with cold starts, or did you keep the serverless functions warm?
Right. So yeah, cold starts can be an issue. In our case, what we do is we do keep the functions warm for a bit to help mitigate the impact of cold starts. But if you're starting completely fresh, like a fresh deployment, you haven't provisioned any name nodes, and there are some cold starts, but these typically don't impact performance for too long. The name nodes are able to populate their caches with hot file system data relatively quickly, and we didn't necessarily notice an impact of the cold starts in the workload performance. Like if you look at the stats here, all of these name nodes that were started here were cold started, and they were still able to get up and running and sustain this burst of requests effectively. So
yeah.
it didn't impact performance too much.
In the throughput diagram or the throughput chart, you had like Ceph FS for a very small number of clients was a little bit better, but I'm wondering if that was a cold start issue.
Yeah, I think for smaller number of clients, I think cold starts do play a bigger role because the number of name nodes that get provisioned is smaller. So like, as the request volume increases, the serverless platform ultimately provisions more name nodes. But also I think it's a combination of cold starts and just having more of these relatively small individual serverless name nodes. You want a higher volume of them to serve requests. So as the number of clients increases, the performance also just increases because there's more name nodes available to serve requests. So there's just sort of a trade-off between, like the scale that you're working at and the performance that you can extract from these like relatively small serverless name nodes compared to their serverful counterparts.
Great, thank you.
Mhm.
Any other questions? If not, I'd like to thank all our speakers today. So thank you, Herbert, Jawad, Aitor, and Ben for some really interesting talks. And that ends this session. Thank you, everyone.
Thank you for hosting. Thank you.
So I think, Alec, Pedro, are we taking a break now?
Okay, so
Let's
no,
have
yeah,
at
go
least
ahead.
5 minutes, right, Pedro?
Yes, we can have 5 minutes break and continue.
Great.
So 11:05 in US and 5:05 in Europe, right? 5 p.m., 5 minutes. No, is it correct? I think so. Yeah, 17 hours.
Yeah.
So if there are, speakers, I made them, I think, speakers co-host or speakers for the next session. If you are speaker for the next session, please, test now your screen sharing. And Pedro, I sent you a link to the first talk YouTube, right?
Yes.
If you want to test it, if you can play back the YouTube video.
I'm going to try sharing my screen. Let me see.
Go ahead.
Yeah. Can you
I
see
see
it?
DIC and now something artificial intelligence.
Perfect.
Do you want to go into full screen? Do you want to test it? Oh, yeah. Yeah. Now it is full screen.
Great. Thank you.
Anybody else want to test?
I want to test.
Go ahead.
Yeah.
I can see your video and
Yes.
by
Let me
screen
share
sharing.
the screen. Sorry,
Bless
excuse. Desktop 2. Oh, yeah, I'm glad we tried that. The Zoom thing is out of my viewport. Let me double click. Works. Nice. Slideshow. Yes. Can you see the presentation?
Yeah, looks very good. Just go to the next slide. Just to be sure you know. Yes, looks great.
Yeah. Awesome. Thank you.
GEDS generating from data. You see the screen, Alec?
I can see the screen. Can you do playback one more time? It was very like if it is loud enough. Yes. Okay.
I did my bachelor and master in computer science.
Okay, I think it is good enough.
Okay, fine. Okay, let's continue with the last session of this WOSC workshop. So we have seen a lot of presentations regarding data management and communication from serverless functions. So since they don't have direct access, many of us, many researchers, we are trying to optimize how we interact with third-party services and indirect communication middleware, like publish subscribe, like data management. So I think we will see a wealth of good research now in this session about this indirect communication. So first session, first talk is, the title is Enabling Publish Subscribe Services on GEDS. GEDS, it was an ephemeral storage service from IBM Zurich. And the presenter is Pesman Nasirifar, that is a PhD from Technical University of Munich. He's doing things on serverless publish subscribe and the rest. Since he cannot attend the workshop, I will replay the video that he has sent to us. So let me share a screen and go ahead with this. Okay. So.
Supervision of Professor Jacobson and Professor Maya, who got our university to the cloud storage project, and I had the opportunity to work at IBM Research Israel in Zurich from February till April 2023 as my secondment under the supervision of Bernard Messler, Pascal Schrobi, and Michael Kaufman, and working on the GEDS General Data Store, which I'm going to talk about it in this presentation. Over the course of my PhD, I had a chance to work on various topics. At the beginning, we had some collaboration with IBM Watson in Yorktown to use serverless computing for creating public subscribe systems on the IBM Cloud. However, most of my work over my PhD has been done on blockchain technologies from two different aspects. First aspect was addressing the lack of existence of simulation frameworks for understanding the potentials and vulnerabilities of existing blockchains. So we created a few blockchain simulation frameworks to study Bitcoin, Ethereum, IOTA, and so on. One other aspect was offering scalability solutions for permission blockchains. Here we created a solution for Hyperledger Fabric using conflictly represented data types or CRDTs. During my stay at the IBM, I had a chance to work on and contribute to the GEDS, the generic ephemeral data store, which is a distributed data store developed by the IBM researchers for very efficiently transferring and storing ephemeral data in the cloud environment. GEDS offers several features and functionalities for easy integration with existing frameworks such as Apache Spark and Ray Machine Learning Framework. And it offers storage on cloud providers such as AWS S3 or Azure Storage. It even offers storage on local memory for very fast access. They showed that by integrating GEDS with, for example, Apache Spark, they can significantly improve the performance of the Spark by enabling different components of the Spark to very efficiently communicate with each other. The way that the GEDS works is that it consists of a number of consumers and the producers. The producers create and write the data, and the consumers read the created data. For writing the data or the object, the producers first have to write the object to the destination, which can be cloud storage like AWS S3, and then afterward have to write the metadata of the object to a central metadata service. The metadata includes the object ID and its size and its location. For reading the data, the consumer first have to go and look up the metadata of the object from the metadata service. And based on that metadata, it can go and directly read the data from the storage. However, as you can see, we heavily depend on the central metadata service for every read and write, meaning that this metadata service can easily be a bottleneck for scalability. In order to improve the scalability and the performance of the metadata service or the MDS, and consequently improve the performance of the GEDS, proposed and extended the MDS with a public subscribe service or a pub-sub service for streaming the metadata to the consumers. The way it works is that the consumers first have to create streaming connections between themselves and the MDS, and then create subscriptions for informing the MDS about the type of metadata they are interested in receiving it. Afterward, once the producer have created the object and written the object to the destination, they inform the MDS about the metadata of the object, and then the MDS performs matching on the metadata to identify the matching consumers, and then push and string the matching metadata to the consumers. The consumers receive this metadata and then update a local cache with their metadata. The purpose of this local cache is that the consumers, when they want to read the data, first they look up the metadata of the object from the local cache instead of going to the MDS to look up the metadata. Finally, we ran a few experiments to quantify the performance gain by enabling the PubSub on the MDS. We used two Spark setups, one with the original MDS and the other one with a PubSub enabled MDS, and we executed 103 queries on the TPCTS benchmark. We observed that by enabling the PubSub, we could decrease the total execution time of the experiments from 66 minutes to 38 minutes, which on its own is a significant performance gain. We also observed that the most significant improvements are for the queries that read a high number of objects during their execution, as you can see in this chart. The reason is that we already populated the local cache of the consumers with the metadata of the objects read during the execution of the queries during the PubSub, which was a significant improvement. Thank you very much all for tuning in, and thank you very much also at the IBM and the Cloud Stars for making this project happen.
Okay, so we finished with the first talk of this session. I mean, he's not here, so he cannot answer questions, sorry. So we must move to the next presentation, that it's Blackbox operators for dynamic data management frameworks. The presenter is Joseph Spillner, that is a well-known senior researcher in the serverless community from the Zurich University of Applied Sciences. And Joseph, you can go ahead and present your talk.
Thank you, Pedro, for the introduction. So I am going to show the talk on with the title Blackbox operators, but the subtitle Apache Calcite Algebra and Optimizer Extension. As we will later see, it has a certain implementation aspect to it. So going to what you mentioned, Pedro, before is the right direction. We are looking at how can such architectures fit into what is in the end the value-adding component in companies, which is making sense of data, integrating data, which sometimes is a bit a boring topic, but we see a lot of excitement recently because data management is becoming more dynamic. It is extensible by functions, and it is moving also towards more hybrid environments, such as hybrid clouds. And here, in particular, we are interested in anything that goes beyond the traditional relational model. We may even think that the time for purely relational systems has come to an end. We are looking in particular at user-defined functions, UDFs, or user-defined aggregation functions, user-defined tabular functions. They have different inputs and outputs. And we want to understand how relational or non-relational are they? Are they always black boxes? Are they sometimes gray boxes? Can we make some sense of those functions in the optimization of the queries? Because in the end, what is of interest to any query is the performance. So we are looking at, could a query optimizer exploit any information about the functions that we have associated to our data integration workflow? And in order to solve that, I have just started a week ago my secondment, and I'm going to explain the first couple of results. So for those of you who are not familiar with Calcite, I will show an example that is more approachable with existing technologies. So here we have an example that uses Apache Spark, that was just mentioned in the previous talk, and calls out to LitOps, deploys some functions in order to bring some additional functionality. So here the function is quite boring. It is just multiplying any value in a column by the constant 2. But we can see that if we do that row by row, if we consider the entire column and we call the function for each row, it may not be the best, most efficient way to do so. If, on the other hand, we submit the entire column, we may run into payload limits. So typically serverless environments have a limit of 1 megabyte of payload. Or we go into a pull model. We say the function pulls the column from somewhere. There are very exciting developments out there, such as Apache Arrow, where we can, on a protobuf level, access the underlying data contents. But this is a very unexplored space, and we need to provide rich information about the function. What is the function capable of doing? And then we can use that information in the optimization. So here we see an example which brings us closer to the database world. And this is no new picture. I think it has been looking like that since the 1990s. Some smart people came up with ODBC or JDBC as an abstraction layer. So instead of every person having to invent its own way to communicate with databases, we have an abstraction layer. But that led to the problem that even though it makes it simpler to integrate applications, each database vendor had to implement the counterpart of the JDBC. So had to speak the protocol, and when a create table or create function command comes in, has to react on that and run the appropriate commands and has to parse the string as well. And so that led to the creation of Calcite as a dynamic data management framework, which is also reusable by all of the vendors of database systems. So Calcite has exploded quite a bit. It is a very active project. It has an SQL parser, a query optimizer, JDBC component, and a lot of adapters. It is also used by many projects. We already saw today some mention of Flink and other big data toolkits. Probably Spark is the only big data toolkit that does not use Calcite. All others pretty much use it. And it is very capable. It can understand many database dialects. So it is a good idea to use such a omnipresent framework to consider the integration of UDFs and other non-relational operators and investigate how this could be done. And we see on the right side a few hints. Overall, such projects that are fast-moving and are relatively recent are not yet well documented, but we see that we can supply SQL hints to customize the resource usage. We can also have custom operator tables and so forth. So I will just present to you the research outline on a high level, because later we have the IBM Israel presentation that goes into slightly more detail and also gives the strategic perspective. So our main goal is to extend the Calcite relational algebra representation and the optimizer for SQL queries coming from data integration flows that may be Airflow or dbt core, something high level, not related to SQL necessarily. And then we parse the syntax tree, come to the unresolved logical plans, look up operators, which includes user-defined functions, and then optimize the query plan before mapping it to, let's say, cloud-specific or database engine-specific physical implementations. And our main research questions here are how to extend the algebra to account for non-relational and UDFs. How can we represent the integration flow? Can we have something like an AFT, abstract flow tree, which is the higher layer variant of an AST for the SQL query syntax? And a third matter, can we implement this in Calcite, and if so, how? Most of the initial work was spent on preparing Calcite for research, making it more approachable. So we see that the initial picture, we still have the JDBC interface, but now we have the Calcite JDBC component behind it, and the main or core Calcite classes that parse data query language, data manipulation language, transaction commands, and so forth. Those are used by the database and big data technologies that were mentioned. But recently also a new component came up called Calcite Server that is able to implement DDL commands such as create table or create function, meaning that for the research perspective, it is great because we no longer need an actual database. We can just submit our commands into Calcite Server, which is like a mock database, and we have it fully under our programmatic control. And here we can come up with our research clients, so to say, both on the CalSite API level and on the JDBC interface. Here we have already found that it may be very suitable to come up with something like a CalSite client as well. If you have a CalSite server, then we may also have a CalSite client in which we can simply define functions in an easier way than the traditional SQL create function syntax permits, and especially create functions that are very scalable, that go out into the internet and run in distributed cloud environments. So here you see a very first result, version 0.0 of our CalSite client. We have defined two functions. One is a local function called square that simply squares a number, and one is a lead ops function that goes to serverless environments and submits values from a database column there. We already see that the projection works, the logical query plan is created. We get some cost metrics that are used for optimizing, and of course we get the correct result as well. And that way the user can already, in a much more flexible way, create expressions dynamically, and that is the expressiveness that is simply expected by data scientists nowadays. They know it from PySpark and from other such frameworks, and we want to bring this to the database level at the very scalable and optimized way. So this is the initial progress so far. The content has just started. I heard there will be a public Git repository, maybe by the middle of July. You will be able to use it then as well. So thank you very much. This was my short presentation. And of course, I'm available for questions.
Thanks a lot, Joseph. Excellent talk. Some questions from the audience? No? Well, I may have one, Joseph. So no, I really think that I really like your proposal about these user-defined functions. When you say user query function or columnars, or you can even have questions that match to queries in data management. So how ambitious is this? Can function as a service become a front end for queries, or what are really the limitations or the trade-offs? I don't know if it's cost or it's volume of data, or what is realistic here?
Well, I think if we look at the left side again, it is getting to the user who is in this universe here, is concerned mostly with data integration flows, and is mostly concerned with, I have a database here and I have a data warehouse there in different cloud environments. One may be a private cloud, one may be a public cloud, and empowering that user to express a query that is able to run where it makes more sense. If the data is in the warehouse, then the function should be brought to the warehouse and execute there. So I think this is where in the longer term, we won't solve all of that during this secondment, but in the longer term, that is where I see this approachability, and combining this with newer research on natural language processing queries. I think I see a lot of potential on this left side. But first we need to resolve this middle side to make the mechanics work.
Really cool, Joseph. I think Alec wants to say something. Alec?
Yeah, I have a follow-up question. So like when kind of what Pedro was asking, so if it is, we have that all working and working great, where would it, you think, used? Like, would it be used in, like, I don't know, cloud providers, open source projects? Who are the target user, or just anybody that installs Apache CalSite somewhere and then use it?
Ideally, all of those projects that make use of CalSite should be benefiting from that automatically. So if you have a stream processing with Flink, and Flink is able to parse and optimize your queries that call out to functions, and consider the function characteristics such as, let's say, cold starts and deviation in response times, and is able to understand that maybe Sunday evening the calling to one function provider is faster than another. Ideally, then, if it's encapsulated in CalSite, all of those database technologies and big data processing technologies should be able to benefit from that automatically.
Okay, thank you.
Nice.
Thanks so much.
Okay, cool. We can move to the next presentation that is artificial intelligence for smart environments. And the presenter is Aurora González Vidal, that is a PhD student in the University of Murcia. And you will be presenting this before your stay in IBM Watson. So go ahead and present, Aurora.
Can you hear me?
Yes.
Okay, great. So, well, thank you for the presentation. My name is Aurora. I'm a postdoc at the University of Murcia, and my work focuses on artificial intelligence for smart environment. This is what I will talk about today. So my research consists basically on two main areas that are related. On the one hand, I develop basic research, or I do basic research. I develop algorithms and methodologies to solve real data problems regarding the reduction of their volume, imputing missing values, and federated and transfer learning. And then on the other hand, I use and adapt such methodologies for another AI-based ones to extract knowledge from sensorized environments in order to create new services that are automatic or improve the existing ones. So the areas of application are IoT verticals, such as buildings, agriculture, transportation, and security. And the developments that I will briefly present here are published already. So the references to those works are highlighted in black through the presentation. And let me start with the first case. For basic research, I will describe the main lines of work. The first one is related to finding optimal ways to reduce the data points of a time series while preserving the key characteristics of the data. So basically, we created an algorithm called bits that, roughly speaking, splits the data into streams, the data streams into blocks, computes the DCT, the discrete cosine transformation, and then makes some more calculations, getting at the end the modulus of the eigenvalues of the final matrix as the representatives of the same series. So comparing classification and clustering results using raw data and the transform data, we obtain obviously better results in computing time, and many times the accuracy was kept the same or even improved in some of the cases. And we have currently submitted work with the multivariate version of this algorithm. Then another line of work related to data problems is missing value imputation in multivariate systems. We have developed a model that is based on Bayesian maximum entropy and allows the incorporation of knowledge regarding how accurate the sensor is, like hard sensors or soft sensors. The methodology accounts for the geolocalization of the sensors as well. And this has been, we have created a web application, and here there are some demos about it. We are also very much interested in federated learning, which has been already introduced in this session or in the previous one. But basically, you know that it enables training machine learning while maintaining machine learning models on a decentralized way while maintaining data privacy. So we have created a multi-class classifier for detecting attack types and applied it in the Tone IoT dataset, for example. We have also analyzed the impact of non-identically independently distributed data. Consider also different aggregation methods such as FedAverage, FedPlus, and also we have worked on differential privacy as well so far. And indeed, we have identified several challenges in federated learning scenarios, and we try to tackle it, some of them bit by bit. For example, at this moment, we're working on defining new aggregation functions and on unsupervised federated methods as well. And finally, as for the basic lines of research, transfer learning is another of my lines of work. And the idea of transfer learning is to use the knowledge gained on specific use the knowledge gained on a particular task in another similar or related task or from a similar domain. We have created a methodology based on, first of all, we cluster the individuals using their metadata, not the dynamic data, but the characteristics. We train some deep network like convolutional or LSTM, depending on the work that is going to be applied on, but some deep neural network using all data of the centroid of this cluster, and then transfer the model to the rest of the individuals of the same cluster. And we show that using less data from these individuals, we still get very good results regarding the prediction and the accuracy. So far we have been transferring the weights of these networks, but we want to try other strategies as well. And as for the second part, or the other line of the other main line of research, which are methodologies to extract patterns towards the creation of smart services in the Internet of Things verticals. Let me describe some of the environments that we've been working with. So first, we have been focusing on improving buildings to make them smart in the sense of energy efficient. We have done energy consumption prediction works using machine learning. We have studied how to select some features, which kind of models like black box, gray boxes, white box are better, time series modeling as well. And we have studied also patterns on the HVAC usage, like the heating, ventilation, and air conditioning, in order to give personalized recommendation to the users according to their profiles. We have used data that is of the type of set points of the HVACs, or how the user intervenes with the set points, how many times a day, how many hours they have it turned on. And also recently we have published an open data set with a year of data from a smart building in Murcia, and also some works on demand response, which is a strategy used to manage and balance electricity demand during periods of great stress. That's for smart buildings. We have also many scenarios in smart cities in general, as it is the case of water management. Here we have collaborated with regional institutions for detecting anomalies in water consumption using traditional statistical methods such as ARIMAS and machine learning as well, in order to find different patterns. Also some strategies to, again, extract knowledge of the data using symbolic aggregate approximation, which can be compared with bits, the original work that I talked about first. Thirdly, smart agriculture is another field where we have had some projects and advances. We have published a framework to deal with all the process from data collection to data fusion and analysis applied to a smart greenhouse. So the idea or the service we provided was to select automatically the climatic systems according to the environmental context. And this platform is connected to the algorithms that are available through APIs created by means of OpenCPU and other packages. As regarding smart agriculture, we have also studied satellite images for NDVI estimation of a piece of land and weed identification using images by means of CNNs, and those works are currently under review. And finally, I am currently focusing on a specific case in my region, that is the creation of a digital twin of a lagoon and its basin that is called Mar Menor. It's a complex ecosystem that we want to understand from a data perspective in order to make realistic changes towards its preservation. And these are the references. that's all. Thank you for your attention.
Okay, thanks a lot, Aurora. Any question from the audience? Well, I may have one, Aurora. So sorry, you are a postdoc, not PhD, my fault. Another. So you are expert on AI, and really next year I see really a confluence between cloud technologies, distributed systems, and artificial intelligence. I mean, Stoica, as always, he discovered this connection one of the first. So he created this CSML conference, and he is, of course, now leading this field. But now that you are an expert on AI and you are going to Watson, can you tell me at least one or two research challenges of combining cloud and distributed systems with artificial intelligence?
Well, I was thinking on basically, apart from the cloud, thinking on this edge, fog, and cloud perspective. Well, one of the challenges that I would like to tackle, maybe now, maybe later, it's about how to, well, it's about tiny machine learning. It's about how to embed the algorithms into tiny systems, and then how to combine it with cloud computing in the right moment, you know. So as you have seen, I focus one part of my research on the applications. So sometimes you need to maybe just detect some kind of anomaly and then send the data afterwards and do some cloud computing. So I think the combination of these is going to be very powerful, and it's going to bring the real smart systems to reality, you know. So I think that's there. And also I am really interested in this transfer learning, I don't know, this transfer learning frameworks, which are again useful for spreading the knowledge. Because for now we work in a use case, we work separately, but I think like if we can connect, if we can connect different environments, different domains, and make use of all this power, again, the emergence of smart environments will be a reality. So I think that's there.
Nice. Nice answer. Thanks a lot, Aurora. Good luck in New York. And okay, next presentation. Now it's.
I think Thomas has his hand up.
Question? I didn't see it in the race.
But your mic is muted.
Thomas, super fast. Go ahead. Yeah.
Okay. Do you hear me?
Yes.
Okay, thank you, Aurora, for the presentation. Nice to meet you again. So we met in Tarragona. Very nice research areas, very compliments to my research area. And I have a question. Have you analyzed the complexity of algorithms and the possibility to deploy this data imputation and time series compression on IoT devices? Because it might be quite time consuming and CPU consuming to process these points.
So we have analyzed for the data compression. Yes, we have analyzed the complexity of it, but we haven't really gone to the point to do it, you know, to try to really embed them. So experiments need to be done, but I think it's really interesting and needed, you know, because the proposal is there, so we need to go further.
Okay, so maybe we can collaborate. And when will you be in US?
I will go. I will arrive on the 6th. Well, I will go the 6th of July. I arrive the 7th, so in a couple of weeks.
So
what about you?
Now I'm in US, so we are coming back on the 10th of July. So maybe we'll meet for one day.
Or maybe not, because I will arrive the 7th at midday. So probably I will just first day will be the 10th.
Okay.
But,
okay, so
anyways,
we'll talk offline.
Yes,
we'll find the place.
Offline.
Sorry.
Okay, thank you.
Thank you.
Bye. Thank you. Bye.
Bye. Thank you.
Okay, so let's move to the next one. That is Kubernetes server localization by Sachindra Talluri. No, if I'm getting it correctly. And then you are a PhD student at Brecht University Amsterdam. So go ahead and present your talk.
Yes. Can everybody see the slides?
Yes.
Yeah. Hi, I'm Sachindra. I'm a PhD student in Amsterdam, as Pedro said. And this is like in this talk, I'm going to talk about the work I'm going to do during the secondment to like IBM Israel. And yeah, it's on like error localization, Kubernetes configurations. I'll explain all those terms. So, okay. So like Kubernetes is like an important piece of software in the like cloud ecosystem, right? So like Red Hat says 70% of enterprises they surveyed use Kubernetes. And I don't think I need to convince this audience of the importance of this system. But a bit more detail about it. So in like a recent analysis of, recent in 2020, an analysis of Kubernetes found that Kubernetes distributions have like up to like 256 unique features. And each of these features have many configuration knobs, like the autoscaler might have some knobs and so on, leading to thousands of configuration options. And these features and configurations change between different distributions of Kubernetes. So Google's Kubernetes is different from Amazon's, is different from IBM's. And they even change between versions of the same distribution. What this means is like the knowledge about like what knowledge about configurations and other things goes out of date really fast. So knowledge on Stack Overflow and GitHub issues. And problems are really hard to debug for users. So usually the end users of Kubernetes might not have like the most knowledge of the internals of how things are implemented inside Kubernetes. So this leads to like problems being hard to debug. So before I go on like how we solve the problem, I want to give a brief overview of the system model of Kubernetes. So in this, like read this from like left to right. So the user supplies some configuration, usually in the form of like YAML files. So Kubernetes reads this configuration and like forms, and based on its internal state at that time, forms expectations. So like what should actually happen for the user's configuration to be realized. So these expectations, then Kubernetes, like in the control loop, acts upon them. Let's say I need to start a container. The expectation will be like, okay, container should exist. The action will be call Docker, start the container. And once it's started, Kubernetes will record the state. And yeah, like that is a control flow. So in this work, we are only looking at errors inside the Kubernetes code base, not because there could be an error passed to like the Docker command, or maybe we set some rules in IP tables for networking, but like they were wrong, not things outside the code base of Kubernetes itself. So like this is an example Kubernetes configuration for a cron job. Like there's a job we want to run like the hello world for Kubernetes. And usually after you like pass a configuration to Kubernetes, there's a result stored inside the in Kubernetes internal state. This is the example structure that's used by the cron job. It's like cron job status. I just extracted it from the Kubernetes source code. So it has references to the actual like job objects. It has the last time the job was scheduled, so on. Now, the thing is, let's say like the job did not run or the last schedule time was wrong. The most likely cause for that is like, the user passed the wrong schedule. So such features usually, let's say you're using some normal programming language to program stuff, right? If something was wrong, then the compiler raises an error. But for Kubernetes configurations, that's not like often easy. Maybe like this example is like deceptively easy, but often it's not easy. So what we plan to do here is, so when user supplies the configuration and the configuration is executed by Kubernetes, we'll track the data flow of how these configuration parameters are passed through the code base of Kubernetes. Then when the final state comes out, so here the actual state is there's an out of memory error, but the desired state is user says, yeah, there shouldn't be the error. We see, okay, like what configurations could have caused this difference? We relate the data flow tracking to the actual like final state change that occurs. But this is not that simple, right? If the user did not pass a configuration parameter, this does not identify it. So what we do is we not only take the configuration passed by the user, But other configurations, right? There are many Kubernetes configurations out in the wild on GitHub or like in people's like private repos. We just like execute a lot of them to collect information about what configuration options can even like influence the final state we are looking at. At least that's the idea. So the data flow analysis, the data flow tracking, for example, this is like some pseudo code. So let's say in the Kubernetes internal code base, like every time the configuration option is read, we like set like a bit, we tag like, let's say like a bit vector. And when the configuration is actually used, we do like a bitwise OR of the bit vector to like just keep the tracking going. Yeah, like the key takeaways from today are like debugging Kubernetes configurations is like hard, especially if you don't know much about the system. And we plan to use dynamic data flow analysis to determine like what configurations options could have caused the error. Thank you.
Thanks a lot, Sachindra. So any question from the audience? Question, I don't see any question. Okay, let me ask you one question.
Yep.
Yes, well, this error localization, like preparing the dynamic data flow, I'm now imagining these kind of things cannot be done by artificial intelligence in the future, like establishing all the flows or inferring which ones are incorrect. Or so. You are planning to use AI to do this, or really is more straightforward that I'm imagining?
That's actually a really good question. So the project like at IBM Research is about like using AI, but also like users' knowledge, let's say like Slack channels or from Stack Overflow to suggest like possible error locations. But my part of the secondment is not about using AI. It's about, let's say there are 1,000 options. It's giving a subset of those options. Let's say, these 10 are most relevant to the AI. So I don't know if you tried using like ChatGPT or something. Sometimes it gives out things that look right, but might need not be right. So the idea is this will help narrow down the possibilities for the AI. So alone, so in the example I showed, I tracked it exactly to the line, right? I don't think the software I make can do that. But let's say I narrow down the configuration options and then pass some information to the AI can do that. So that's the bigger idea, yes.
No, cluster configuration in a Spark or in Kubernetes can be completely crazy with hundreds of parameters and prone to errors.
Exactly.
Yeah. No, it's an important problem. Thanks a lot.
Exactly. So
let's move to the next talk. Multi-cloud support for GEDS. And the presenter is Luis Veiga, that it's a senior researcher at IBNESC ID in Lisbon. So Luis, you can go ahead.
Thank you, Pedro, and thank you, Alec, for the opportunity to present. Okay, so this is work done during the secondment at IBM Research Labs Europe in Zurich in the hybrid cloud research group led by with the work led by Bernard Metzler. Okay, so we are witnessing now an increasing interest in multi-cloud, okay, and the opportunities are many of them, okay, are several. So mainly federating cloud resources, okay, from different cloud providers and even resources available at the edge, but also allow access to scattered data while avoiding excessive replication of the data in multiple cloud provider storage. And this way, maybe you can reduce storage cost. When we went to IBM, the idea was to study ephemeral storage systems for cloud computing, namely the GEDS system that was already addressed today at least twice, okay? And okay, it was a good opportunity to study an architecture of one such open source system, and it's a big system. It's a system with a lot of development already on it. So we discussed some optimizations regarding the architecture of the metadata and caching support, and some of them were applied or adopted by the colleagues there. But okay, just for this talk, we wanted to address the multi-cloud support for GEDS. So currently, GEDS only has one metadata server, okay, that runs the metadata, and the main workload on GEDS, as it was already mentioned today, is to transfer ephemeral data that is generating during big data workloads. So to avoid lots of interaction with the cloud storage or with the persistent storage elsewhere in the distributed file system. But eventually it needs to spill data to cloud storage when local resources go out. Okay, so what did we wanted to do? Okay, we wanted to make GEDS work on multiple locations. When metadata server running on each of the cloud locations, on a different cloud provider or on a different cloud cluster, so that one single MDS would not become the performance and the scalability bottleneck. Recall that MDS by itself holds no data, but it's the coordination point that every worker needs to interact with in order to find out where the files are located and then get the data directly from other workers. So what we did was we branched the Golang implementation of MDS that was going on, being developed by Peshman, that was a colleague of ours at IBM then, okay? And we federated the metadata servers. So in order to enlarge the metadata namespace and to mediate the metadata lookup across different clouds, so that the clients need not be modified and become able to interact with different or several MDSs at the same time. We didn't want to change the implementation of the clients. And at the same time, distribute the pub/sub system extension, okay, so that we could also distribute the subscription management and the event propagation. Okay, in a nutshell, what we did was, okay, we federated the metadata server, so now each MDS registers with other MDS instances when it starts or when the user wants. It serves its own metadata, okay, file, object, and buckets, but at the same time, it operates as a gateway for any operation that requires access to metadata that is being managed by a different MDS instance. And this way it relays the requests to other MDSs. So now MDSs don't need to deal with a lot more clients. They just need to deal with a limited number of additional clients that are other MDSs representing maybe a lot of worker nodes on their own location. And this way, there is no single MDS that becomes a scalability and latency bottleneck. At the same time, since we now have different MDSs running in a federated way, we can also extend the distributed subsystem that was developed. And now each MDS manages subscriptions of its own workers, okay? And also manages combined subscriptions from other MDSs that in essence represent all the workers that are interested in a given file or a given bucket and that are initially connected to that remote MDS. When there is an event that is triggered or it needs to be published, the MDS propagates the event in parallel to all of its workers that have subscribed, and at the same time propagates the event in parallel to all the other MDSs that are acting on behalf of other interested workers running on different cloud locations. This is still just functionality, okay? It's hard to test this in different cloud locations to see if the added latency is let's say it's a showstopper or not. But okay, we have ongoing and future work. One main work is optimize multi-cloud transfers. Now we have direct cloud transfers, but we can leverage the cloud provider's own networks to make this faster and even cheaper, okay? Maximizing the usage of internal paths owned by the private networks of each cloud provider, and having a smart way of mapping nearby DCs of different providers. We also developed a tracing API for GEDS. Now that it is a distributed metadata service, we developed a tracing API to allow studying of other policies and performance gains in a structured way. And we also want to optimize the metadata and the handle of the data itself, caching small files, caching metadata at workers. This is already undergoing or even implemented in MDS. And we would also like to push newly written data to readers, to really pipeline data that is being produced to whoever is consuming it without the need to even store it as a whole in the ephemeral storage. That's it. Thanks very much, Pedro and Alec, and I would like to thank Bernard, Pascal, and Michael. They were great in hosting us, and also thank my colleagues there, and Radu, okay, the team leader, and also thanking our colleagues there, René, Aitor, and especially Peshman, which was with me, one of the two first cloud stars, as Bernard put it, because we were the first secondees. Thank you very much, everyone.
Thanks, Luis. Nice presentation. Any question from the audience for Luis? No, so maybe I have one, Luis. Nice that you enjoyed there in Zurich and you could collaborate with them. And my question is about this. So you design like a multi-cloud layer, and really I think like this Stoica with the Sky computing, they are really trying to study this data transfer between the clouds. But can you explain us like one use case or application where it makes sense to have data in many data centers and then to have, because if it's ephemeral in GEDS, it is difficult for me to imagine a case where you have some functions accessing ephemeral state, but can also serve with functions with ephemeral state in other cloud providers. So can you give us a
okay. It's not necessarily to spill ephemeral state to a different cloud provider, but imagine that you have some workload that you're running and it needs from input as input, or it needs to generate as output, but especially needs as input, data that is stored at a different cloud provider and is being managed or is being generated as another workload managed by another MDS. Instead of replicating the entire data sets, with this, you can just propagate the data that is really being accessed at the other location. We can't access the data exclusively locally. We can't ship functioning, but it would even be a great optimization, and it would prevent issues with, when you don't want to share your entire data, but you still want to allow people to execute workloads on some data sets. This could be an enabler for that, this line of work.
I see. It's like an intelligent data tier that can really select or move data according to the needs to the application. Still, I think that you would require from the application developer to give you some like data management or data movement requirements or data access patterns or analyze the application in order to create this intelligence in the data layer. No, so you still require some help from the application.
Yes, but I think that we should not force programmers to change their code. But if we can encode that in some kind of configuration for the MDSs when the applications are run, we could specify policies, preventing these specific files from being fully sent to another location, or just allow access to the data that is being streamed by. I think. With the MDSs federated, you can enforce some level of simple policies without needing to change the applications. That was something that we didn't want to do, force the programmer to have an additional set of parameters or an additional set of API methods, because otherwise we couldn't test it with the workloads they already had with the benchmarks.
Yeah, no, super interesting. Now, multi-cloud was in the future things that serverless had to go. And you are imagining the future now. So you are saying how it will be done, this multi-cloud thing. So it's cool. Thanks, Luis, a lot. If we don't have
thank you very much. Thank you, everyone.
Thanks. So we move to the next one. Now we have only two remaining presentations from two senior IBM researchers. And if you are planning to move in a secondment to these IBM locations, it is interesting what they are going to explain us. Now, the next one is serverless activities in IBM Research Israel. Ofer Biran, which is also a senior researcher and project manager leader there in IBM Israel, will explain some of the serverless activities that you are offering to research stays in your location. So thanks, Ofer. Go ahead.
Okay, you see okay my screen and hear me okay?
Perfect.
Okay, I had some internet glitches, so I hope it will survive that. So I'm Ofer Biran from IBM Research Israel. I will tell you one slide about our lab and the four related activities that are part of the CloudStar's Staff Exchange projects, and these are the cloud observability, multi-cloud data pipeline optimization, multi-cloud networking. Pedro mentioned multi-cloud. This is a major focus in IBM today, and the efficient serverless model serving. So the IBM Research Israel, and actually the nice building you see here is in Haifa, and you see on the map Haifa, but we do have multiple locations like Tel Aviv and Beersheba in Israel, and actually Joseph that talk is in the Tel Aviv branch. We like to call it branch because, you know, Tel Aviv is the big city and Haifa is the province, and at least in research in IBM, we are the center and they are the branch for this. So it was pioneered in 72, contribution to IBM leading products, open source, extensive collaboration with the academy, and the extensive EU participation in EU projects. And we like to say that we are in the middle between the academy and the industry. So we are a good place for research. So the first activity, and these are activity areas that two of them already have a secondment active and planned, as you will see. It's a cloud observability. And this presents really the ability to monitor, analyze, and get insights for things that happened within the cloud. And without it, you're kind of blind with where your things are running on the cloud. Also, without the cloud, observability is important, but this becomes critical on the cloud days. The special focus in this area of observability that is in the context of the CloudStar's activity is observability-based Kubernetes configuration profiling. Kubernetes, as Sachin already told you, is a very important thing, definitely for IBM after the Red Hat acquisition, as you know, with the OpenShift version. And it has a huge configuration space, and most of the problems happens to be configuration issues. Our objective is to provide a path from observability data into the configuration knowledge that we have. So the solution approach is to train a model of the Kubernetes issues from public repositories, from internal repositories of support data and so forth. And as part of the secondment, and this is what Sachin described, getting expert knowledge about the configuration with a kind of a training with a dynamic methods to get a path from the observed data to configuration aspects. And then when there is an observed event coming, we will correlate it and enrich it and filter it to better creating a prompt into the resolution extractor that will get the matches from the model and provide actionable resolution to users that in turn can be turned in a feedback loop to get a better answers. So we have Sachin that will start on 2nd of July, and he described what he's going to do. We hope that it will be very successful, and good luck, Sachin, for that. The second area is multi-cloud data pipeline optimization, where in what we call the multi-cloud data pipeline, it moves data, and Pedro mentioned the things that relates to data and AI. So you have data in one place, and you need to process it in another place, definitely now in the AI days. And In a flow, there are sources like Postgres, targets like the Snowflake in Azure, and you can specify a transformation. And there are a lot of the questions. The recent questions are in optimization. What transformation exactly? Where to run it in the source or the target? What metadata to collect in order to be able to answer on these questions? And here we have the secondment of Joseph, that the focus, the project definition, at least, in the beginning of the secondment, is to extend the Apache calcite algebra and the optimizer to be able to handle the Blackbox UDFs. And I will not repeat. As Joseph is progressing, I'm sure you will get updates for this. And this is, I think, an exceptional secondment of a senior researcher. That is unusual for us in IBM. We used to get a PhD student, and I think it's a very interesting experiment, and blessing and good luck to that. The overall questions would be how to extend the relational algebra, and will we be able to address all operators, and how exactly to apply it to the calcite, and envision the output is actual demonstration and code change, and of course the publication. The third area is multi-cloud networking, and multi-cloud is effect now. All it's not now; it's even in the last years that all enterprises are in a multi-cloud environment because of acquisitions and because of specialized cloud. That it's better to do this on that cloud and so forth, and cost, of course. And the current network models really, if you have an enterprise with these multi-cloud scenarios, the current solutions are not enough, and it impose a huge configuration burdens and coordination, because unless you get one network provider that gives you the all pictures and the ability to apply your enterprise policy and so forth. So the potential project in this area is to research building of building blocks facilitating multi-cloud networking that will, and this really relates also to serverless functions that can used as an accelerator, providing this high availability and in-network computations, and really network services to control for the control and data plane functionality, and VNFs are definitely a solution. The desired skills for this is, of course, basic understanding of networking. The AI always blessing today, and definitely hands-on capabilities in Kubernetes and the serverless world. The last activity area is what we call efficient serverless-based model serving, and where we have a cluster with limited resources. Of course, GPU is the most important resources today, and there are multiple services that are using multiple models to provide the inference. And these services can use one model or a workflow of using several models to arrive at the answer. And the research is how to scale and optimize such a cluster to come to a optimal throughput. Definitely GPU is the key element here. It dramatically accelerates the model inference, but they are very expensive and more limited resources. So the tricks that must be used is GPU sharing for multiple models, either on a spatial way or temporal time sharing or combination. And of course, the batching and smartly prepare a batch of requests for getting parallel answers. So these are the activity areas. As I said, the first two already have active secondment and a planned one, and we are looking for more collaboration, and I'm sure that we'll have that. So any question, I will be happy to answer and to, ready for additional collaboration for the next secondment within the clusters. Thank you.
Thanks a lot, Ofer, for your nice talk. Really hot topics. I'm sure that they are super interesting for many people willing to move. So this will be recorded and we'll distribute this to all partners. And we have flexibility to move. So these topics in multi-cloud, observability, and everything sound super interesting. I don't know, any questions here? No? Just one question, Ofer. When you say multi-cloud, it's because it's going beyond multi-data, multi-region. So you are connecting to all clouds, even Amazon, even Google. So IBM is now willing to develop technologies that interconnect to other cloud providers?
Yes, IBM definitely is ready to provide, but this is about the multi-cloud functionality that is offered to IBM enterprise customers, and they are in the situation that they already use multi-cloud and get a lot of problems synchronizing all their multi-cloud applications. So we want to help them.
Okay, because for example, with Stoica, this SkyPilot thing is mainly about cost engineering. Is about telling which one is the cheapest one to run.
Well, it's part of the possible support, and we are involved with the SkyPilot with Stoica, and this is cloud brokerage, and you want to offer, but I'm not sure that this is the most critical functionality to get the the cheaper place to do your processing, because there are very serious governance issues and where data can be moved and many other issues. But this is of course one of the issues.
Yeah. So if cost engineering, so if cost improving is not the goal for multi-cloud, which challenges do you foresee, like one or two in multi-cloud research?
The governance regulation about the data movement, that you have your data in one place, but the best GPU cluster is in another case. So you need something like the Skyplane, for example, to efficiently move data and to process it. And there are a lot of optimization questions about it and things like that. And coordinating the network between your things on the multi-clouds and apply policy on your network. There are many questions that arise. And multi-cloud is actually the extension of what we used to call hybrid cloud. And hybrid cloud is kind of a special case of the multi-cloud.
Even about programming abstractions, not to really make transparent the deployment in any cloud of your code.
Right.
Nice, super nice topics. So, okay, last presentation today is from IBM Zurich. It's Bernard Metzler, that is also a senior researcher in IBM Zurich, and he's also presenting the interesting research topics that they can offer to secondments. So let's go for, I will put his video because he couldn't connect today. So let me now put his video. Okay, one moment. Okay, you see my screen now? Yes, so go ahead.
Not yet.
You need to share your screen, Pedro.
Sorry, yes, no, I have two screens, so here, now you see my screen. Okay, so.
Wait, no, we don't.
Not yet. Try again.
Sorry. So, one moment. Yeah, I know what's happening here. Okay, one moment. It's now you should see my screen.
We can see Slack.
Okay. So now you should see my screen.
Yes.
Okay, now I can start. So this is the last talk today, and let's go ahead.
Hello, everybody. This is Bernard Metzler from IBM Research speaking, and I'm going to present you potential research opportunities at our lab in the context of the European Cloud Stars program. I will start with a short introduction of our lab in Switzerland, and then cover some potential areas of collaboration, including ephemeral data handling, but also other potential activities. In the end, I will give you a summary and contact information for people who are interested in joining our team. Our lab maintains a long history. It was established in 1956, and we are hosting researchers from more than 45 different nationalities. We are known for our open collaboration. For example, within the European Horizon 2020 program, we are participating in more than 50 funded projects. We are worldwide recognized with 2 Nobel Prizes and the Cartley Prize in 2016. We are chosen as one of the European Physical Society historical sites. We are partner with the on-site nanotechnology center, and we were chosen for 7 European Research Council grants. Our lab maintains a large diversity of scientific fields, including artificial intelligence, quantum computing, life science, mathematical science, and more. The activities of our team can be located in the field of hybrid cloud research. The next slide summarizes our research activities and fields relevant for the Cloud Stars program. First of all, we have a focus on infrastructure support for serverless and granular computing. That is, we want to build distributed systems from a virtual cloud resource continuum by focusing on elasticity, resource optimizations, and achieving bare metal performance by using modern networking infrastructure and hardware. In that respect, our current focus is on storage and communication scheduling components, including flexible storage provisioning for ephemeral data handling, resource-efficient, location-aware task scheduling, and multi-cloud or Sky computing principles. Our potential activities include GPU deployments to provide software-based file system storage solutions, machine learning-based self-tuning of distributed systems, and software-based quality of service optimizations for FLEdge-based storage. So, why do we think we need the generic ephemeral data handling? First of all, ephemeral data handling dictates overall computer frameworks performance, as you can see on the right side. Second, ephemeral data handling consumes storage, computing, networking resources, so resource efficiency is key. Nowadays, compute frameworks implement deeply integrated private solutions, for example, Apache Spark's block manager or Ray's Plasma data store. Typically, these solutions are DRAM-based and spill over to local disk. Typical problems of that approach are the lack of resource disaggregation and elasticity, which prevents independent scaling of compute and storage according to current workloads. Furthermore, there is no efficient data pipelining among concatenated frameworks possible. With that, our goal is the unified efficient handling of ephemeral data for analytics and serverless frameworks. Short provides storage disaggregation and multi-tiering, independent elastic scale-in and scale-out of compute and storage, and the efficient coordination and communication among tasks and jobs. We prototyped such an envisioned data store, which we simply called GEDS, a generic ephemeral data store. That data store offers the following features. It is a multi-tiered object store. It seamlessly integrates with multiple frameworks. It provides resource disaggregation and elasticity. It provides zero-copy local data access in tier 0, independent scaling of compute and storage, and it enables efficient data pipelines between frameworks. As you see on the lower left side of that slide, the prototype is available as open software at GitHub. The following slide provides a summary of all the GDS-related activities which may be interesting for you. I do not read them out all in detail here. You can just stop the presentation and look for yourself. Thank you. Now, switching gears, we are also active in the field of efficient resource management and scheduling. With Mira, we are developing a resource management for fast, efficient serverless application execution and intelligent scale-out. Mira is an intermediary resource manager for distributed application frameworks such as Apache Spark. It sits between an application and another resource manager, for example, FLEnative. Mira caches worker pods and/or executors in pools for reuse by applications. With that, it avoids long resource allocation delays and cold start penalties. It enables fast resource acquisition and release. Furthermore, we are also active in another field, which is the deployment of data processing units. In that respect, we are developing a software-defined file system service offload. While today, networking and block storage offloads to data processing units is already available, there is no such current solution to do file system offloads. Missing that, each tenant in a virtual file system must implement and maintain its own complex file system clients, such as NFS. The project offloads the file system to the DPU, and it exposes the service via Virtual FS implemented at the DPU. Currently, we are prototyping the design of such a file system offload at NVIDIA BlueField 2 DPUs. In a completely different area, we are also active in the field of machine learning-based self-tuning of distributed systems. The problem at hand is that many complex systems have many tuning knobs, and unoptimized configurations can be highly suboptimal. The solution to that is the development of a machine learning-based tuning framework that automatically optimizes configurations for target workloads and hardware. Applied to FoundationDB, our prototype yields performance improvements of 35% compared to the default parameter settings. Last but not least, we look into software-based quality of service optimizations for flash-based storage. Today, solid-state disks have low average latencies, but also exhibit high tail latencies. This is because I/O latencies do not include full physical data storage retrieval costs. Writes are cached. Writes produce fragmentation, requiring cleanup work in the background. Data might get relocated due to re-leveling. Additional metadata I/O may happen at the same time as reads and writes. That accumulates to latency tails when user I/O must be throttled. The goal of that project is to significantly reduce tail latencies. To summarize this presentation, the potential research fields of CloudStar's assignees include the following: ephemeral data handling, scheduling, DPU deployments, machine learning-based self-tuning of distributed systems, and software-based quality of service optimizations for flash-based storage. Please contact us. We are happy to have you here at the IBM Research Zurich Lab. Thank you for your attention.
Okay, so we finished with the last presentation in this workshop. So Alec, I give you the floor to finish this WOSCx2 workshop. Thanks.
Yeah, so the one thing I would like to say is that it is not really finished, I hope. We will continue conversations, and we will be putting online the video recording of the workshop. So if you want to talk to people, it should be very easy to review what different areas of research are happening. And you all have access to Discord server, and you should also sign up for the mailing list if you are not. And hopefully we will have more opportunities to meet online or even in real world in future. So that's all that I have. And this is now open for any questions or anything you want to bring up. And I can finish recording if you want to say something off the records.